Okay, good morning, everyone. Uh, okay, I don't know am I audible or not. So, anyone please unmute yourself and tell me am I audible or not, so that we will start the next topic. Yes, am I audible?
Yes, sir.
Thank you. So, in a,
Yes,
okay, 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 it's all right. Okay, so in the last lecture, we have started three-phase inverter, not even start, but just we have seen the circuit diagram and the load even, right? So three-phase inverters, as we know that single phase inverters are normally used for home appliances or at the institution or offices for just for backup purpose. Uh, but in industry, these single phase inverters are not used because these single phase inverters are low power inverters. So when we required high power, we don't have any other option than three-phase inverters to be used. So for high power applications, three-phase inverters are preferred. For low and sometimes medium power application, we can use even square wave. And in square wave inverters, we are not getting a pure sine wave. So that is another disadvantage of a single phase uh, inverters. That is, they cannot be used for high power applications. And second thing, the single phase inverters will produces a square wave or a quasi square wave, even not a sine wave. And even after connecting some filter or wave shaping circuits, the output waveform of a single phase inverter is not close to the sine wave. So these are some disadvantages of single phase inverter, most important for high power application and even for pure sine wave. So sine wave, pure sine wave, even in three phase inverter, we are not getting pure sine wave, but very close to the sine wave, or we can simply search after some modification in the output waveform of three phase inverter, we can achieve, we can have maybe a sine wave or close to sine wave. So as compared to the single phase, three phase inverter produces a more, maybe you can say sine wave output voltage. And second thing, the output power, if you want to uh, control the AC drive, three phase AC drives, then definitely we require a three phase inverter. Even three phase inverters are for high power applications. So this is a circuit for three phase inverter. In this circuit, we are using six switches: S1, S2, S3, S4, S5, and S6. Dear student, again remember that these switches are nothing but the power devices. For simplicity, the symbol of a switch is shown here, but these switches are nothing but the power devices. Okay, so power devices may be a power BJT, maybe a power MOSFET, IGBT, JTO, or SCR, right? For a power output power greater than 5 kilowatt, we are always prefer SCRs. Below 5 kVA, we can use any other power devices, but above 5 kVA, we cannot use these power devices like a power MOSFET, power BJT, IGBT, or other devices. We don't have any other choice above 5 kilowatt, so we always use SCRs for high power applications. Okay, so symbolically they are shown here as a switch, but my dear student, these are the power devices, right? When this switch is closed, we can say that the power device is turns on. If this switch is open, we can consider that the power device is turns off. Okay, so keep in mind these S1, S2, S3, S4, S5, and S6 are the power devices, right? For better understanding, hello, for better understanding, these devices are replaced with the switches, so that you can easily understand when the switch is on and when the switch is off. So if this particular switch is closed, we can consider that the device is on, right? If the switches are closed, then we consider that the device is on. One more thing, every device, if it is power BJT, power MOSFET, it required a triggering circuit. So again, triggering circuit is not shown here for simplicity, maybe to avoid the complexity in a circuit diagram. And even protection circuits are also required. That is also not shown in the figure, right? Even protection from high voltage, protection from high current, or maybe a rate of change of high voltage, a rate of change of high current, or sometimes temperature, heat sinks or cooling method, etc., which are not shown here in the figure for avoid the complexity of a circuit diagram. But keep in mind, these are the requirements. Okay, so only by using six switches and one battery, you cannot maybe construct the actual three-phase inverter circuit. This is basically a block diagram, we can say, of a three-phase inverter. Okay, so triggering circuits are not shown, then protection circuits are also not shown in the figure. Okay, so you can write even in your answer for the complexity, to avoid the complexity of a circuit, the triggering circuits and protection circuits are not shown in the given figure. Even for better understanding, the devices are replaced with the symbol of a switch, so that we can easily understand when the switch is on and how the current will be flow. Because if we told that the switch is on, right? But if we are using device like a BJT or MOSFET, so we cannot understand how the switch is turns on. But here it is very easy. When these particular 2 points connect together, it means it's a switch is on, right? So just for understanding, the devices are replaced with the switches. Now, as per the syllabus, only resistive load, and that is a star connected load, is a part of your syllabus. But both type of loads are shown here. First one is a star connected, and second is dead delta connected load, right? So any kind of load you can use it, but as per your syllabus, resistive type star connected load is mentioned, properly mentioned in your syllabus. So three-phase load that is shown here. So it is, you can consider that this one, that is a star connected load we are connecting here. Okay. Now diodes which are connected in the circuits are not required even. So in this three-phase inverter circuit, uh, these diode D1, D2, D3, D4, D5, and D6 are not required for resistive load. Okay, but that is connected because the same circuit you can use for inductive load, so that these diodes are kept as it is. So we connect the diode as it is, no problem, but you can write here for resistive load there is a no use of diodes, but for inductive loads already we have seen that what is the use of these diodes, right? Because you everyone knows that the use of diode D1, D2, D3, D4 in case of single phase full bridge inverter with inductive load, right? So this is about the circuit diagram. You can see here this first part nothing but a one half bridge inverter. The second part, that is a second half bridge inverter, and this is a third half bridge inverter. As we know that in half bridge inverter, there will be a S1, S2 only, and two diodes. In full second half bridge, third half bridge. So three phase inverter, nothing but the combination of three half bridge inverters. Okay, so already you know that the working of first half bridge, maybe a second half bridge, third half bridge. So all are the half bridge inverter. So working is already known for half bridge inverter. Now we just combine these three half bridge inverter so that we will get a three phase inverter. Again, a voltage source. So it is a voltage source inverter, right? And we are connecting load that is resistive. So this is about the circuit diagram. Now the same thing is written here for your understanding. Three phase inverters are used for high power applications such as AC motor drives, induction heating, uninterruptible power supplies. A three-phase inverter circuit changes DC input voltage to three-phase variable frequency, variable output voltage. The DC voltage can be taken from battery or maybe rectified AC voltage. Normally, rectified AC voltage is used because every time to use the battery is not possible. So whatever the supply voltage available with us, we convert that to the DC voltage, and then that DC is used as an input to the inverter so that you will get a variable voltage and variable frequency at the output of inverter. Okay, so this is very important. DC voltage from the batteries, that is DC source, or you can say battery, or a rectified AC voltage. So this is very important. Normally batteries are not used because it is not convenient uh, to use the batteries every time. Okay, so rather to use batteries. Rectified AC voltage. Rectified AC voltage means the AC voltage which is available with us, that is used to apply to the rectifier, or you can say three-phase converter, and after conversion of AC to DC, that DC is used as an input to the inverter circuit. Okay. A three-phase bridge inverter can be constructed by combining three single-phase half-bridge inverter, already discussed. Figure shows in above slide the basic circuits of three-phase bridge inverter. As showing, it consists of 6 power switches with 6 associated freewheeling diodes. The switches are open and closed periodically in a proper sequence. This is again important. Proper sequence to produce a desired output waveform. The rate of change of frequency, switches determine the output frequency of inverter. As already we know that the on time of switches decreases, then overall frequency increases. If on time of switches increases, the frequency of inverter decreases. So that already we know that. Now this is again most important. Basically, there are two possible schemes of getting the devices. In one scheme, each device, that is a switch, conducts for 180 degree, and in other scheme, each device conducts for 120. So according to that, these two are divided in 180 conduction mode and 120 conduction mode. These are the two conduction mode or maybe a scheme. But in both these schemes, getting signals are applied and removed at every 60 intervals of the output voltage waveform. These modes of device conduction are described in the following subsections. So this particular bridge inverter, three-phase bridge inverter, works in a two different operating modes. One is called as 180 conduction mode, another is called as 120 conduction mode. These both conduction modes are very important. So in examination, there will be a question on 180 or 120 conduction mode, right? So in 120 conduction mode, each device is conducting for 120. So at 120, your output voltage is equal to 0. And in 180 conduction mode, each device conducts for 180. So output voltage is equal to 0 at 180 degree or alpha, right? In 180 conduction mode, if your alpha is 0, you will get maximum output voltage. Then you can increase alpha 10, 20, 90, 100, 150, 170, so that your output voltage decreases, decreases, and decreases. And at 180 degree, your output voltage becomes 0. But in 120 conduction mode, each device conducts only for 120 degree. So maximum firing angle available is 120. So you can change your firing angle from 0 to 120 only. At 120, if your firing angle is 120, your output voltage is equal to 0. Okay. In both these schemes or cases, each device or getting signal applied to the devices is removed at every 60 degree. It means that one device is turns on, another device is turns off, and so on. But the getting signals are applied after every 60 degree interval. So keep in mind, if device 1, 2, 3, threes are on, so maybe one device is going in off state, another device coming in on state. So after every 60 degree, there will be a triggering pulses are applied to the switches. Okay, so that is basically called as a that is 60-degree interval, right? So we will see 180 conduction mode first, and then we will see 120 conduction mode. Okay, now I'll just show you 180 conduction mode and uh, the operation table. Okay, then we will see the output waveforms. These output waveforms are not possible to fit in a single PPTs, so try to understand these waveforms, because somewhat it is uh, change. I think this will be here. Okay, so we have to adjust this thing, because not possible to cope up these waveforms exactly in a one PPT, but I'll explain you in detail each and every waveform. But before that, I'll just show you, this is the operation table. Now what is operation table? So in interval first, this is first interval, we can say, right? This is the first interval of 60-degree, first interval, this is the first interval. Okay, so you can say first interval, see that is written here actually, first interval. Okay, in this first interval, the conducting devices are 5, 6, and 1. Incoming device is 1, outgoing device is 4, right? Outgoing device is 4 because in a previous case, that is the last case, you can see here, 4, 5, 6. These devices are conducting. After that, case 1 will be followed. So 4, 5, 6, 4 is outgoing device, 1 is incoming device. So 1 will be added here and 4 will be removed, right? So that is why it is called as a incoming device and outgoing device. Okay, so just see the last stage, sixth stage, in which the device 4, 5, and 6 is on. 6 is incoming because in previous state, in previous interval, 6 was absent, right? 3, 4, 5 was conducting, so 6 was absent, right? So 6 is coming in interval 6, right? And 3 was the outgoing SCR, which is present in a interval 5, so that is outgoing. Similarly, in case first, device 1 is incoming device, and device 4, that is the device conducting in state number or level interval number 6, that is outgoing device. If you understand this, then I will maybe proceed further, right? So there are total 6 intervals. Okay, total 3 devices on at a time, 1 from upper arm, 2 from lower arm, or 2 from upper arm, 1 from lower arm. So we'll see the first case, 5, 6, 1. Just see the diagram. 5, 6, 1. See, 1 is upper arm, 5 is upper arm, and 6 is lower arm. Okay, so these are the 3 switches turns on, right? So what happens, from this EDC, current start to flow through S1, then A, and then it goes to the phase A. Similarly, the same voltage, positive voltage, flows through the 5, then switch 5, then C, and then this one. So at this time, the phase A is positive and phase C is also positive. But phase B, in which the current flowing from the phase B, then 6 switch, and then back to the negative terminal of battery, right? So this is a negative voltage actually, right? And these are the positive voltages which are coming. So 2 voltages coming from S1 switch and S5 switch, and current leaving from this particular load, that is through the switch S6 back to the battery. Okay, so these 3 switches are conducting only for 60-degree interval, only for 60-degree interval. S1 is on, S5 is on, S6 is on for 60 degree. Just see here. First interval 5, 6, 1, incoming 1, outgoing 4, right? Now check the output waveform. See, the gate voltage 1 is applied for S1 switch, right? That time the S2 switch is off. Check here, S2 is off. In next cycle, S2 is also on, right? You can check here. initially in first case S1 is on, that time S2 is off, S3 is off, S4 is off, but S5 is on and S6 is also on. These are the three switches which are on during first interval. You can check. These are the gate pulses. Gate pulse to the 1 is on, 2 off, 3 off, 4 off, only 5 is on and 6 is on, right? So in first interval, the gate current applied to the S1, S5 and S6, right? Next, that this time what happens? See, the output voltage, that is phase A. This is called phase A or phase voltage EAN. Phase voltage EAN is positive and it is equal to EDC by 3, right? It is equal to EDC by 3. Okay, then this time phase B is equal to minus twice EDC by 3, because the voltage coming from phase A and phase C, sorry, phase A, voltage coming from phase A and phase C leaving from phase B. So phase B equal to minus twice EDC by 3. Check here. Phase A is positive, the voltage level equal to EDC by 3. Phase C is also equal to positive, the voltage equal to EDC by 3. Okay, EDC by 3. Phase C. This is about the phase B and this is about the phase C. Okay, so this is EDC by 3. Then the voltage here twice EDC by 3 and here it's again a EDC by 3. Okay, so these are the voltage levels. This is also EDC by 3. So these are the three voltage levels we get during the first interval when S1, S5 and S6 is on, right? You can check here the equivalent circuit. I'll show you later on, but we'll go for the second level or interval when S1 is on, S2 is also on and S6 is on. 5 is outgoing SCR or device and 2 is incoming device. Now again check the circuit diagram. I'll just remove this one. Okay. Now S1 is already on, S6 is already on. Now incoming device is S2, S5 is off, then S2 is on. Now we can check here in this interval, that is interval second, in which S1 is on, that is from upper arm, only one device is on, and in lower arm there are two devices, S6 and S2, both are in from lower arm, both are on, right? So S1 is on, S2 is on, and S6 is on. You can check here the triggering pulses. S1 is still on. Now S2. In previous case, interval 1 when S2 is off, but now this time S2 is on. Now S5 is turns off because the gate bias is removed, and S6 is also on. Okay, S6 is also on. Just a minute. Just 1 minute. Sorry for interruption. Okay, so in this second interval, S1 is on, S2 now turns on, S6 is remains on, but S5 turns off, right? This time we can check here the voltage, that is A voltage is equal to twice ADC by 3, right? Then voltage at B phase is equal to minus twice, sorry, EDC by 3 only, and here in ECN it will be equal to minus. So B and C voltage is same, but phase A voltage is twice EDC by 3. Similarly, at third level, fourth, fifth and sixth level, you can check here in third interval, interval number third, that switch S1, S2, S3 is on, 3 incoming, 6 outgoing. See why the notations are given like this. That is S1 here, S2 here, S3 here, S4, S5, S6. See, you should keep in mind and you can simply remember this thing, because otherwise it is very difficult to explain the working with this particular table, right? So as per the table 561, then 612, 1, 2, 3. You can check here. The device 1 is on for 180, right? This first interval for 60, second interval for 60, and third interval for 60. So device 1 is on for 180. That's why it is called as a 180 conduction mode. So device 1 is on in interval 1, 2, and 3. Okay. Similarly, device 2 is on in interval 2, 3, 4. Similarly, device 3 is on in interval number 3, 4, 5. Device 4 is on continuously for interval 4, 5, 6. Device 5 is on for interval 4, 5, and 1. And device 6 is on for 6, 1, and 2, right? So every device is on for 180-degree, right? But after every 60-degree, one device from the conducting devices, out of three devices, one is turns off and new device may be turns on. So after every 60-degree, triggering pulses are applied to the devices. Okay. So one device may be called as outgoing device. So that device turns off and another device enter into the sequence, or you can call conducting devices. Okay. So this is the table. You can explain the working of this circuit with the help of this table and these waveforms, right? So these are the voltage waveforms for 180 conduction mode, right? And these are the these are basically called as a phase voltages, and these are line voltages. So EAB is a line voltage between phase A and phase B. So it is equal to EDC. You can check here the addition of these two voltage A and B, right? So addition of these two voltage will be the EAB, then EBC, then ECA, and remaining three line voltages that are not shown here. But this is the equivalent circuits, right? So in interval first, what happens exactly and how the voltage levels are find out. Okay, that we have to show here. That EDC, EDC by 2, and so on. So these waveforms, see, this is the theoretical part for your reference purpose. Okay, so circuit diagram, you can understand the working with the help of this table. Can I say that you are maybe definitely understand this working of this circuit with the help of these waveforms? Now the level, voltage level, twice EDC by 3, EDC by 3, minus twice EDC by 3, how it will happen, how these voltage levels are find out, that we will see later on. I will show you with the help of equivalent circuit diagram. But with the help of this operation table, do you understand the working of this particular circuit, these operating table and waveforms? If you understand, then I will go for the next. Okay. So anyone from you unmute and tell me, do you understand the working of three-phase bridge inverter with the help of operation table and voltage waveforms? These are the triggering waveforms. Then second one, line voltages, phase voltage, and third waveform are the line voltage. How this EAB is calculated, EBC calculated, I will show you with the help of equivalent circuits. Don't bother about that. But just simple working with the help of operation table. If you understand, then we will go for the next. So anyone from you, just tell me, do you understand the working of this three-phase inverter with the help of this operation table and these waveforms? Don't see the levels. I will explain you the 2 EDC by 3, then EDC by 3 minus 2 EDC by 3, how it comes, that I will explain you with the help of equivalent diagram. But just see here, during first interval, 5, 6, 1 is on, 1 is on, 5 is on, and 6 is on. Remaining 3 SCRs are off, right? So 1 that is not conducting in a previous pair, so it is called incoming, then outgoing. Now 1 is there for 3 consecutive pair intervals, interval 1, interval 2, interval 3. 1 is on, 1 is on, 1 is on. Now in interval 3, the interval 4 basically, 1 outgoing, it means turns off, right? 1 turns off. Here in interval 1, 1 enter into the conducting pairs, and it conducts for next 180 continuously, and in fourth pair or fourth interval it turns off and one device turns off. Okay. So do you understand the working of this bridge inverter with the help of this operation table and the waveforms? I'll explain you the levels, but just see interval 1, that time the voltage EAN is positive, EBN is negative, and ECN is also positive, right? Then in next interval, EAN is still positive, EBN is still negative, but voltage level is decreasing, and ECN it from positive to negative. So these levels changes. How it changes? See here, this particular circuit diagram, right? So when S1, S5 and S6 is on, that time the current flows from EDC S1 to the phase. So phase A is positive here because current coming, right? Similarly, S5, then C. So C is also positive and current leaving to the particular load from S6 to the load, right? So S6 is negative, right? So you can check here in interval 1, A is positive, B is in interval, sorry, BAN, right? Okay, so in B is negative, so that is twice DC by 3, and C is also positive. So C and A is positive and B is negative. Okay, that I will explain you with the help of these equivalent circuits. So these are the three equivalent circuits shown here. During first interval, right, these are the resistors. Basically this is a load, that is a star connected load. This load actually, I'll just show you the load. This is a star connected load. So equivalent diagram of this is shown here. See, A phase is on, A, C and B. Okay, so this is RA, RB and RC. These are the three resistors. Okay, now in this particular equivalent diagram, the incoming current is I1, that is coming from EDC and enter into these two resistors RA and RC, and from neutral the current going to the back EDC. So we can say incoming currents and this is outgoing current at the terminal or node, you can say N, right? So I'll just show you here these three resistors RA, RB, RC, right? Now you can check RA and RC is a parallel resistors. Okay, so RC parallel RA, total R equivalent equal to RB plus RA parallel RC. These two are parallel resistors. Okay, so total resistance is equal to RB plus RA parallel RC. Okay, now if we consider RA equal to RB equal to RC, then it will be 3R by 2. The equivalent resistance is called as a 3R by 2. Okay, now current I1, current I1 equal to EDC by R equivalent, EDC by R equivalent. Okay, this is current I1, EDC by R equivalent. So EDC by R equivalent is 3R by 2. So current I1 equal to twice EDC by 3R, right? Current I1 equal to twice EDC by 3R. Now EAN equal to ECN equal to I1 into R by 2. That is basically a equivalent resistor, and EBN equal to minus I1 into R, only R, 1, or you can say RB, right? These are the parallel combinations. So EAN equal to ECN equal to I1 dot R by 2. R by 2, say RB parallel RC, right? RA parallel RC, RA parallel RC. And if we consider RA equal to RC, then it will be equal to R by 2. Okay, so this is a parallel combination. So current, the voltage called as EAN and ECN both are same. So that voltage equal to I1 current into resistor R by 2. So it will be equal to EDC by 3. So in this particular interval, EAN and ECN both are equal to EDC by 3. Check here. This is EDC by 3 and this is also EDC by 3. Okay, in this waveform, EAN and ECN both are EDC by 3. Now, last one. EBN equal to minus I1 because current is reverse, maybe current leaving from N. So it is minus I1 into R. R is nothing but your R. So minus I1. I1 is equal to twice EDC by 3R into R. So it will be RR get cancelled minus twice EDC by 3. So check EBN voltage in output waveform. So EBN equal to minus twice EDC by R. Sorry, twice EDC by 3. This is the level. Okay. So this voltage is find out from this particular equivalent circuits. So this is EBN and this is EAN ECN for interval first. I think a very short time is remaining. So you will start to give your attendance in a chat box immediately till I'll explain the next circuit, that is the circuit in interval 2. Everyone start to give your attendance. Last 2 minutes are remaining. So second interval. In second interval, we can check from the table. In second interval, 6, 1 and 2 is on. 6, 1 and 2 is on. So I'll just show you the 2 is on, 6, 5 is off. Okay, 6 is on and 2 is on. Okay, so incoming current is only A. So S1 is positive, but B is negative as well as C is also negative. Right? So this is the condition. Now check here. C and B are parallel. Okay, C and B are the parallel. Now see the equivalent circuit diagram for phase 2. C and B are the parallel. A that is in series with this parallel combination. Right? Now again same thing. R equivalent equal to 3R by 2. Okay. Now current I1 is incoming current through this. This is incoming current and leaving current is actually this was slightly wrong. Okay, this battery should be like this. Okay, so incoming current is R and leaving current is B and C. Okay, that is negative currents, we can say. I'll just show you again. This is a positive. Okay, now the current, there is incoming current, you can say called I2, that is incoming current at the point node, and outgoing current from N to this one. Okay, so what happens here? I2 equal to EDC by equivalent, that is same equal to twice EDC by